Bias, a toolbox for benchmarking structural bias in the continuous domain. A paper published recently by IEEE Transactions on evolutionary computation. So what is structural bias and why is it important we can detect and analyze structural bias? Structural bias, or SB, is when an optimization algorithm is biased to certain parts of the search space due to its mechanisms or hyperparameters. This is unwanted behavior in black box optimization, as the location of the optimum can be anywhere in the search space, and therefore an optimization algorithm should only be steered depending on the function it optimizes and not by the algorithm design. To test for structural bias, we first need to decouple the algorithm and the problem landscape influences. For this, we use a special function we call f0. f0 returns a random uniform number between 0 and 1 for any given input. Running an optimization algorithm many times on f0 should give us therefore a uniform distribution of optima over the search space. If this distribution is not uniform, we speak of structural bias. To make it concrete, if an optimization algorithm does not suffer from structural bias, using a two-dimensional search space and running an optimization algorithm 500 times on f0 would result in a random uniform distribution of found points. On the other hand, if the algorithm is for some reason biased towards the center of the space or towards the boundaries of the search space, for example because of a strange mutation operator or a boundary correction method, the resulting distribution reflects this behavior. In order to experiment and validate the use of the proposed bias toolbox, 194 parameterized structural bias scenarios are implemented, ranging from very strong and weaker forms of bias and covering 5 general structural bias types: center bias, bounds bias, clusters, gaps, and discretization. In order to effectively detect structural bias with a relatively low sample size, like 500 optimization runs, we utilize 36 per dimension tests and 32 across dimension statistical tests. Using the p-values of these statistical tests corrected for multiple testing, we can conclude if the distributions are uniform or not and visualize the distributions for extra visual inspection. Using the rejection data, we can then use a random forest model to predict the type of structural bias when present. The bias toolbox can be easily installed and used to help you with algorithm analysis, algorithm design, and choosing less biased or non-biased hyperparameters for your experiments. We share all code, images, data, and trained models on our GitHub page, and the toolbox can be installed with pip in just one line. We also present at Gecco the deep bias extension of our toolbox, which provides pre-trained deep learning models that can detect and predict the type of structural bias faster and more accurate than the statistical tests. We also use explainable AI techniques to visually explain where the structural bias occurs, which gives you a visual way of inspecting the results. See the paper for our results and try out the toolbox yourself.